experimental buffers as well as paper chromatography of amino acids. Alright, now buffers, as I've already shared with you in the recorded video, and as I'm sure you've already learned about in analytical chemistry, consists of a weak acid and its conjugate base, or a weak base and its conjugate acid. Buffers resist changes in pH. In today's experiment, you're going to see for yourselves exactly just that. You're going to add amounts of strong acid, amounts of strong base into a buffer, and you're going to measure changes in pH, which results from such. Now, the addition of a strong acid does not cause a lot of change in pH because of the reaction of the strong acid with the weak base. For example, if you have acetic acid, CH3COOH, acetate buffer, CH3COO minus. Now here is your weak acid. Let me get a better whiteboard marker.
Basta lumabas ng once eh. Hindi ko pa nga, yung isa lang kilala ko sa mukha eh. Kasi wala pa ata siya.
So the addition of a strong acid like hydrochloric acid will lead to a reaction with the acetate. In the process, produce acetic acid. And chloride ion. Remember, hydrochloric acid is a strong acid. So what do you notice? The acetate, the weak base, neutralizes the added strong acid. That's why strong acid was not able to lower the pH of the solution by a lot. Now, what if you add strong base? Like say for example, sodium hydroxide. When sodium hydroxide is added to the mixture, acetic acid, which is the weak acid component, reacts with the added strong base in the process, produce water, as well as sodium acetate. In this case, the addition of a strong base did not cause a significant increase in the pH because the added strong base is neutralized by the acid component of the buffer. Notice that addition of strong acids or strong bases to just a sample of water causes a significant change in pH because there is no such acid, weak acid, or weak base that is available to neutralize the added strong acid or strong base. Is that clear? Buffers are important in living systems because we maintain the pH of the cell around 6.7 to 7.4. The two most important buffers are the sodium carbonate, bicarbonate buffer, which is buffer found in the blood. It's not the only buffer in the blood, but it's the primary buffer in the blood. Now, the dihydrogen phosphate, monohydrogen phosphate, it's another important buffer. That buffer is the one that is used primarily by the cells. So you have the carbonate, bicarbonate buffer system found in the blood primarily, and then you have the dihydrogen phosphate, monohydrogen phosphate buffer system, which is used by the cells to maintain intracellular pH. Right? Okay. Now that'll be experiment number 1, experiment in buffers. Experiment number 2 will be all about amino acids. We're going to perform paper chromatography of amino acids. Now paper chromatography is an example of thin layer chromatography, and this is not the first time we have performed such. vapor chromatography, or TLC of caffeine, right? Okay. Now, amino acids are the building blocks of proteins. We're going to learn more about this in the lecture, and I'm sure I've already shared with you a lecture video about amino acids, right? Okay. So amino acids have an alpha carbon, you have a carboxylate group, you have an amino group that exists in the protonated form, you have an R group, and you also have nitrogen. Now the R group, it is the alkyl group or the side chain. That R group or side chain is responsible for the differences in the characteristics of the 20 different amino acids. Remember, all amino acids, all alpha amino acids, this is the alpha carbon. All of the alpha amino acids have a carboxylate group, COO minus, have an ammonium group, NH4 plus, and have a hydrogen and a side chain bonded to the alpha carbon. Remember that in some textbooks you will see this written as a COOH and see this written as an NH2. But of course, in the discussion that I shared with you, you have learned that due to the acid-base characteristics of such groups, the carboxylate or carboxylic acid ionizes to produce a carboxylate, and the NH2, the amino group, exists in the protonated form, the pH of around 7. Okay? Now, in today's experiment, you're going to observe the different reactions of the amino acids, right? You're going to detect the presence of the amine group, for example, or you're going to experiment with the side chain, right? Okay. Now, there is a reagent called ninhydrine. Ninhydrine is an organic compound that reacts with an amino acid. Specifically, the ninhydrine reacts with the amine group. So if you have R prime and H2, or even if that's NH3, you're going to produce the luminous purple, right? You're going to produce a purple product. I'm not going to write the structure of the purple product because that's one of the questions in the guide questions, right? So this purple product indicates the presence of what? Amines. Now, does the amino acid have an amine group? Yes. Amine group that is protonated, it's okay. The ammonium group still will undergo reaction with the ninhydrine reagent, okay? So, what is the ninhydrine reagent? It is a general test for the presence of amino acids. In fact, it's a general test for the presence of amines. Amino acids react positively with ninhydrine because amino acids have an ammonium, okay? Now, what else? In today's experiment, you're also going to try to detect the presence of the amine groups, alright? Now, sodium hydroxide reacts with an amide, say for example, you have R prime and H2. This is an amine. Now, this is an amide, right? Now, this essentially leads to the formation of ammonia gas, right? And of course, sodium carboxylate. Okay. Now this ammonia, what is this? This is a base, right? So what you're going to do is you're going to heat sample of an amino acid. The amino acid asparagine or glutamine. Asparagine or glutamine has the following structure. Okay. COO minus, NH3 plus, have hydrogen, have here CH2, C double bond O, and H2. Now what is this? This is glutamine, the amino acid glutamine. So we're interested with this, the amide. Now, the reaction of the sodium hydroxide with the amide will lead to the formation of a base. Now, that base is ammonia, right? And what do you know? That is a gas. So if you have a test tube, say for example, that contains this substance, you're going to see the release of the ammonia gas, right? Now in this test, what you're going to do is you're going to put here, what is this? Moist pH paper, or I think you might be asked to use litmus paper. You can use moist or just the litmus paper itself, because the vapor that's going to come out of that already has water vapor, and you have the ammonia. So once the ammonia comes into contact with the red litmus paper, this should be red, what will happen? It will turn blue because it is basic. The ammonia is a base. Do you understand that? So that's one of the tests that you're going to perform today. Now another test that you're going to perform will be the test for aromatic groups. Alright? Now some amino acids react with the reagent that generates a yellow colored product. Nitro or nitric acid reacts with benzene or aromatic rings. Right? Nitric acid right here. Nitric acid reacts with, say for example, this is just an example. Okay? You have here R. Now, this will produce silent. Now, these products are colored yellow, right? Okay. Now, this test is a test for aromatic rings, alright? Okay. Now, which amino acid has an aromatic ring? Tyrosine, right? Phenylalanine, tryptophan has aromatic rings. So if you test these amino acids with nitric acid, you're going to end up forming yellow colored solutions, right? So that's one of the tests. There's actually one other test you're going to perform. That's a test for the sulfidyl group. In other words, the test for cysteine. Now, aside from performing these tests, you're going to perform paper chromatography. Okay? Now, this is not the first time that you have performed chromatography. As I've mentioned earlier, you have performed chromatography back in organic chemistry, right? When you perform chromatography on caffeine. Isn't that true? Right, okay. So, in chromatography, what do we have? We have a stationary phase as well as the mobile phase. What is our stationary phase? The paper. In our case, we will be provided with filtered paper. Alright? Now, the paper chromatography, that is the stationary phase. In paper chromatography is the filtered paper. Now, what is our mobile phase? The mobile phase is the solvent, right? The solvent system. So what's going to happen is you're going to immerse, just going to write it. So we have here, for example, a beaker, right? And you have here your liquid, right? This is your liquid. This is your, this solvent. Organic solvent. This is your mobile phase. Now I'm not sure, hopefully you remember, but you typically spot solids. You typically spot your analyte here, right? Spot it there. Why are we doing this? In order to introduce our material. So in our case, these are amino acids, right? Amino acids. Now, let's say for example that we're talking about this particular amino acid. That amino acid will distribute itself between the stationary phase and the mobile phase. Now, what is the stationary phase? It's paper. Paper, as you're going to learn more about in the future, is actually made up of cellulose. Now, cellulose is a polysaccharide, and it has a lot of, I'm going to write it here this way, it's a lot of hydroxyl group, alright? So what does that mean? This is a very polar substrate, okay? Now, what did I mention about the mobile phase? It's an organic solvent. Yes, it contains water, it has an alcohol, like say for example, butanol, and some other organic compound. But compared, or rather, that means that in comparison to cellulose, organic solvent is polar, but it is less polar. You understand that? Less polar than the stationary phase. What did I mention earlier about the amino acids? How do they differ from each other? The amino acids differ from each other in their what? In their side chain, in their R groups, right? Some amino acids have polar side chains, like what? Aspartic acid, like what? Arginine, like what? Lysine, like what? What else? Did you not watch and study the lecture video that I shared with you about amino acids and PI? What other amino acids are polar? Serine. Okay? Serine. Now, other amino acids are more on the non-polar side. Phenylalanine. Alright. Tyrosine is polar, but it has an aromatic ring, so it's less polar. What else? Tryptophan is also one less polar substance, amino acid. So, depending on the polarity of the amino acids, the spot will either migrate far or will migrate only a short distance. You understand that? Which will migrate farther? The more polar or the less polar amino acids? The less polar amino acids. What did we say about the filter paper, the stationary phase? It is very polar. So the more polar amino acids will dissolve, quote unquote, or will interact more with the stationary phase. Do you understand that? And will therefore migrate only slowly up of the paper. What happens? This solvent will migrate up due to capillary action. Alright? And it will dissolve or carry with it the amino acids. But only the less polar amino acids will migrate or will be dissolved more in the mobile phase than in the stationary phase. Why? Because the mobile phase is less polar. It will interact more strongly with the less polar amino acids. Is that clear? Okay. So, say for example, this one migrated just up to here, this one migrated here, this migrated that distance, migrated that distance. Let's say this one migrated here. Let's say there. This one migrated here. And this one 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, in our experiment today, we're going to have what we call standard amino acids. In other words, these are the known amino acids. You know what they are. And you're going to be given unknown amino acids. Okay? Let us say that this one, AA1, AA2, AA3, AA4, amino acid 4, AA5, and AA6. Right? Are we standard amino acids? In other words, you know what they are. And these three are the unknown amino acids. Alright? Let's say this is U1, U2, U3. How do we know the identity of our amino acid? In today's experiment, as usual, some of you were my students last summer. So you're going to give me 1/4 yellow pad, and you're going to write I'm going to write it on the board. The group number, experiment number, and you're going to identify your unknown. So, how do we know what our unknowns are? Okay, remember, there is what we call a quantity called RF. What is the RF? Retention factor. It's the distance traveled by the analyte divided by the distance traveled by the solvent. Alright? Okay. Now, what is our analyte in this case? Amino acids. Right? Now, the solvents would have migrated up, say for example, reaching this height. We call this the solvent front. Alright? The solvent front. Is that clear? Okay. Now, what are you going to do? You must have a ruler with you. Do you have a ruler? Very good. So you're going to measure the distance traveled by an amino acid. Say for example, your amino acid traveled up to this point. Silence. You're going to look at the center. Locate the center and measure the distance from that center, or from their starting point. If your starting point, I should have written the starting point here. If your starting point is here where the spots are found, then you have to measure the distance from the center of that spot up to the point at which you have marked it or you have spotted it. Do you understand that? That's the distance traveled by the animal. The distance traveled by the solvent is the solvent from distance from the solvent from the start. Okay? Now, how do we know which is which? You're going to match the RF values of your unknowns with the RF values of your standards. So in our case, sometimes eyeballing will let us know which is which. For example, unknown one looks like this. I mean, it traveled almost the same distance as this amino acid. So whatever this amino acid is, what is that? Amino acid 4, that must be your unknown 1. Unknown 2 traveled a distance that is similar to what was traveled by amino acid 5. So your unknown 2 must be amino acid 5. You understand that? And here, unknown 3 traveled a distance that is comparable to amino acid 1. So unknown 3 must be amino acid 1. Do you understand that? But of course, remember, I always ask for a reason. In your reasoning, you're going to write amino acid. For example, unknown 1 is the same as amino acid 4 because their RF values are almost equal. And you're going to write their RF values to convince you. Do you understand that? Okay. Now, earlier I mentioned that the distance traveled by the amino acids depend on their polarity. So, basing your answer on the distance traveled by amino acid 1 to amino acid 5, to amino acid 6 rather, which is the most polar and which is the least polar of these amino acids. Okay? The least polar amino acid is the one that traveled the farthest. In other words, it's amino acid 6, whatever that is. Now, which is the most polar? Amino acid 1. Alright. Now, do not think that these amino acids are not polar. All amino acids are polar. In fact, they are charged. You can see there, have charges. They are charged. What we're talking about is which among these is least polar and which is most polar. And that polarity is determined by the identity of the R. Do you understand? Okay. Now, group 1, raise your hands. Okay, group 2, group 3, 3. Why just 2? Where's group 3? Just 2? Should be 3, right? Or 4, I can't remember. What about group 4? 5, 6, 7, 8, 9. Are you just one? 9. Okay, 10. Okay, 11, 12. All right. Now I want you to post your schematic diagrams here, right? So that I can see those. Okay. Remember, proper laboratory attire. Okay. Now, have you chosen who your group leader will be? Who is your group leader? Alright? Do you all have your laboratory manual? Yeah. You must have your laboratory manual. Okay. Now, what else? Listen, I was informed that we're going to be given just 8 pH meters. Why? Because apparently there are also nursing students who are going to perform the same experiment, same as ours. So what we're going to do is, remember sometimes these pH meters don't work. So what we're going to do is 6 groups will perform experiment 1 first, alright, while the other 6 groups are performing experiment 2 first, and then exchange. Those who performed experiment 1 will then perform experiment 2, and those who perform experiment 2 will perform experiment 1. In order for us not to run out of the pH meters. Why just 6? Because maybe we don't know. Maybe out of the 8, only 6 will function properly. Right? Do you understand that? But the pH meters will be given to groups 1 to 8. Okay? It will be your accountability. So if you partner with, for example, group 1, where are you going to give your pH meter? Which group? Group 7. Okay? Now, group 2, you're going to give it to group 8. Now, if something happens to the pH meter, just to the pH meter, which groups are going to be responsible? Groups 1 and 7. Groups 2 and 8. That's the accountability. Alright? Alright. Now, I'm going to assign you places. So, okay. We need this. Group 1 should be, no, this is mine. So, group 1, 2, 3, 4. Okay. 5, 6. 5, 6. 7, 8. Eleven, 1 to 6, your chemical should be here. Groups 7 to 12, your chemical should be here. Put all of your bags under your benches. Okay. Now, who's the monitor for today? 1 and 7. Monitors for today. 1 and 7.
Walang sa'yo, wala.
Pwede ka po mag-ibig.
Okay lang.
Alam mo,